All right. Hello, everyone. So we are going to ease our way into lecture series number 8. It's a relatively short lecture series because it's meant to be a continuation of our discussion of, machine learning techniques, which was done in lecture series or as part of lecture series number 7. And as mentioned towards the end of lecture series number 7, our specific focus is going to be on 3 subcategories of machine learning techniques. So we're going to look at linear regression, and classification, which are both classic examples of supervised machine learning. And then we are going to look at an example of unsupervised machine learning, which is clustering. Specifically speaking, we're going to focus on k-means clustering. In terms of the outline of this lecture series, the vast majority of really content to be covered is best understood by by going through the Jupyter notebook, which has been uploaded onto the Google Classroom site. So I do encourage you to find time to do that. But we're just going to briefly look at some specific things associated with regression, classification, and clustering as part of the theoretical discussion of the lecture series. I'm going to suggest that we perhaps find time in addition to Monday to have a discussion centered around the Jupyter notebooks that I have shared in the event that people have questions. And I think what would be interesting is if we have discussions that would be centered around the respective projects, the mini projects that you are currently working towards or working on. All right. So yet another reminder that we're using the CRISP-DM model as our guide, and we are still at a stage where we are discussing, model implementation and evaluation. The reason why we have, model implementation and evaluation highlighted is because if you remember in lecture series number 7, we mentioned that the evaluation process is typically conducted in 2 main phases. So during the development, as you are trying to identify the optimal configuration associated with the model you're implementing, trying to determine the best feature combination that you should use as you're implementing the model, the best estimators that you would want to use, and in some instances, the hyperparameters that would be associated with either the estimators or perhaps the weight embeddings that you'd be using. All that happens to involve some aspect of evaluation. Of course, after successful implementation of the model, you'd have to conduct a final evaluation of the model itself by comparing the results of the model relative to the original business goals, which would have been identified as part of business understanding. So again, our focus here in terms of the model implementation is we're saying the end goal is always to define the model components, the features, and how the model is ultimately going to behave, and of course how you go about interpreting the model itself. The evaluation would typically involve you assessing the various alternative techniques that can be employed to implement the model, and then of course subsequently comparing the model with original business goals or objectives. The end goal, obviously, irrespective of the technique you're using, is you're interested in finding patterns in the data, right, to gain some sort of insight that will help you make important decisions. So you could be, if you remember, you could be predicting something, or you might be interested in trying to extract or identify patterns hidden within the data. So when dealing with prediction, you typically find yourself working with either linear regression or classification. So in terms of regression is generally a technique that will involve the prediction of one variable from the other, right? It's if you remember, we said a classic feature of regression, the thing that sets it apart from classification, for instance, seeing as both of them are supervised machine learning techniques, is the fact that you'd be predicting a numeric variable, a quantity, so a number. Can we predict the final score that a student is going to get at when they write the exam, for instance? Can we predict the salary increment of, let's say, an IT manager 2 years down the line, depending on what sort of factors we take into account. In essence, this is it involves statistical modeling that we evaluate the relationship between a variable, between one variable and one or more other, variables. So this relationship really is aimed at trying to identify the association that would exist between the thing that you're interested in measuring, which is the outcome. If we were to visualize the outcome using the simple equation y is equal to fx, for instance, what we'd be saying is the y. What we're saying is the y is the dependent variable, the thing that you're measuring, and the different combinations or permutations associated with the x's would be the independent variables, right? So really this statistical modeling involves using one variable, which is a dependent variable, the final outcome, and a series of input variables, which are independent variables. So this would be, the features would be independent variables, and then the dependent variable would be the final outcome, or the label in this case. You typically use a single equation for determining this relationship, and of course the final form of the equation is dependent on the series of variables that you'd be using, right? In some instances, you might want to scale up certain variables using predefined or identified factors, right? And we'll see how this plays out actually as we are going through the Jupyter notebook. Yet another thing to point out here is that this equation, the final form of the equation, is also highly dependent on the total number of independent variables that you're working with, right? So if we are interested in, let's say, predicting a student learning outcomes, and the only feature or data attribute that we are using is, let's say, the gender, for instance, of the student, that's a classic equation that just uses it's a univariate equation. You only have one variable there, and so the only thing that you'd be doing is perhaps either adding a constant to the equation itself, fx, or maybe scaling up the variable by some constant, right? So you use this single equation really to determine the relationship that exists between the dependent variable and the independent variables. This would be a classic y is equal to mx plus c equation. Actually, that's what we're referring to here. So that y is equal to fx could be also viewed as being equal to y is equal to mx plus c. So a variable is nothing more than a factor, right? That can take on a value, right? And in our case, we are really associating this variable to the different data attributes, right? Those are the variables we're referring to. And a reminder here that these variables will be associated by different characteristics in terms of the variable types. So they could be numeric, it could be categorical, or they could be ordinal. An important point to note at this stage is that by the time you're deriving this equation, and you don't do it by hand, but by the time you're deriving this equation, you would be working with the transformed version of the variable. And this is really interesting because if you find yourself, let's say, working with a variable y is equal to fx, where the x is, let's say, the gender, for instance, right? Male or female. Well, in this case, I mean, we could probably come up with a very simple equation where the x variable would just, plus some constant or something, the x variable would just be it would just be a representation of whether this is male or female or something, right? Whereas if we're working with an equation where, let's say, the x itself is the, let's say, the course minor, right? We have English, we have maths, we have civic education, we might have geography, for instance. because the transformation, right? In this case, I mean, we don't really have to worry so much about the transformation because we know that. Well, I mean, we'd have to one-hot encoding. We encode this, but you don't necessarily have to worry so much about the transformation here, right? You can just have this value hold 0, 1 to represent male or female. But when we get to a stage where we are working with a variable that can hold more than 2 values, right? It's not dichotomous in this case. The transformation would entail employing one-hot encoding. And so when we one-hot encode this, would be faced with a situation where this variable would have to have the variable E, I guess, right? M, C, and G as well, right? So you notice that it kind of like, it gets somewhat complex. And the complexity increases when these X's, you know, would entail you having additional variables to work with. Let's say the input variables include gender and the minor, right? So in addition to these 4 variables, would have to include another variables that would represent gender. If we are adding Moodle interaction logs, you notice that the equation kind of like, you know, gets complex, right? Either way, this complexity, you don't really have to worry so much about this complexity because it can easily be automated, and you use software to do this actually. So the dependent variable is the thing that you're measuring, right? Or the variable that you're observing, the final outcome in this case, whereas the independent variables would be the factors, right? Or the data attributes that you would be manipulating in order to observe the desired outcome. So the idea here is, if you think about what's happening from the perspective of a labeled data set, that labeled data set will have different variations of input variables, right? If you look at gender, the different variables will hold different values for gender, right? So as you are tweaking or as you are changing or manipulating those independent variables, you would be observing the effect that it would have on the dependent variable, the thing that you're measuring. Yeah, so as a difference there. So what you do as part of linear regression really is you fit a linear model to the data that you're working with. So this would be the independent variables and dependent variables, and the dependent variable is usually continuous or numeric in nature. So given a set of points, given a set of points, right, representing the labeled data set, would be interested in finding a linear function, right, that goes through the points, ideally, right? Usually this would, for the most part, it could be a straight line, but in some instances it may not be a straight line. So that straight line will represent you a generic behavior associated with the variables linked to the data set that you're working with. That would be the labeled data set. So just showcasing an example here of the linear equation, right? So if you notice, would have derived this linear equation in this particular example that is linked to, this would be linked to the outcomes that we get, right? When we feed the input, when you feed the independent variables to this linear equation. Of course, depending on the type of problem that you'd be solving, this straight line may not necessarily pass through all the data points, and this is the reason why evaluating the final model becomes important, right? As part of evaluation, if you remember our discussion lecture series number 7, we had mentioned that you use techniques such as the mean squared error or the mean absolute error, right, to try and evaluate the effectiveness of the model, right? So essentially, you'd be trying to measure the extent to which the actual outcome deviates from the computed outcome, right? So in this particular case, what we'd be doing is we'd be saying for each of these attributes, right? I'm sorry, for each of these data points, this, for example, this data point here is the actual value, right? Whereas the point that lies on this line, right? So we have a best fit line here that we've drawn. The point that fits on this line here, which is somewhere here, would be the actual value. This is the observed value. So our interest is to measure the difference, right? This difference between the actual value and the measured value. And we do this for each of the points, right? So you think of what we have here as being a representation of our test data set. Yeah. So we draw a best fit line representing the model that would have implemented, and then the actual values associated with the test data set would be used to evaluate the performance of the model. If you remember, once we have this data set, we split it up into training and testing. The training is the one that you use to derive this best fit line, right? This is the model, whereas the testing would involve you trying to measure the errors associated with the different data points here. And so the different techniques that we use to measure the error. So be it mean absolute error or the mean squared error, what we're doing is we are computing this associated error by finding the distance between the data point and the straight line. So the observed value is subtracted from the predicted value, right? Of course, in the mean squared error, you'd square the results, and then you get the average. You average them out afterwards. Whereas in the mean absolute error approach, what you do is you just get the absolute value, because the differences from this point on the straight line to the actual value might be negative or positive. So in this case, all of these data points that fall below the line would entail that the difference would be negative, right? Because the value that is on the line is greater than the observed value. Whereas for these points that fall above the line, the result of you subtracting the predicted value from the observed value would be a positive value, and hence you have a situation where as part of you computing the mean squared error, you square the difference, whereas with the mean absolute error you just get the positive value, right? You get the absolute of the difference. So in addition, obviously, to the mean squared error and in addition to the mean squared error and the mean absolute error, you have the sum of squared errors also, right? And I think you typically would use this as input. No, this is a different metric actually. So just showcasing a specific example of a metric that we didn't really introduce in lecture series number 7. This is the sum of squared errors, but the idea is the same. So what we're doing with the sum of squared errors, you notice here, is all we are doing is we are getting the difference between the observed value and the predicted value. We square it and then we sum them, right? And the idea behind this metric is you notice that if you have a situation where the cumulative sum, right, or if this metric is smaller, then your model is performing better than when this value is larger, right? A larger value entails that there's a very huge variation between the observed values and the predicted values, right? In other words, the points, right? The points, the actual values, the observed values will be further away from the best fit line, which is something that you try and avoid, right? And in fact, when you're implementing these models, what you end up doing is you end up making changes to the model. As part of the implementation of the model, you'll be tweaking either the hyperparameters or maybe alternating the different feature combinations so that you have a situation where the variation is minimized. Variation between the observed values and predicted values is minimized, essentially, which happens to be the goal of linear regression, to try and minimize the error. And then in terms of classification, if you remember our discussion in lecture series number 7, what we're doing is we're predicting a categorical variable, right? So it could be predicting whether someone is eligible to vote or not, whether somebody is eligible or qualifies for a loan or not, whether we are predicting if a particular candidate is going to win an election, or perhaps whether we are predicting if somebody is going to pass or fail an exam, for instance. Right? In all these different instances, we are predicting a category as opposed to a numerical continuous variable, which is what linear regression does. There happen to be different variations of classification. So if you think about these categories we're predicting from the perspective of the different attributes we discussed last time, right? If you remember, we were looking at a situation where we can have, dichotomous attributes like male versus female, right? Pass, fail, right? Or you can have a situation where you have more than two categories, right? So the prediction of these categories could either be that you are predicting either of two values, right? Or you could be predicting predicting more than two categories, right? Or two values. So a classic example from the data set we're working with is maybe you want to predict if somebody is going to get an A plus, a B plus, a B, a C plus, a C, a D plus, or a D. So in this case, we're no longer just dealing with two values, right? It's like multiple values. So in situations where you are predicting two variables or two values, you'd be dealing with binary classification. It's yes, no, right? Or 1 or 0 something. So binary classification just entails that the dependent variable can hold either of two values, right? Whereas multi-label classification would involve is it you predicting or classifying more than two categorical variables. Sorry, these are supposed to be alternated here. So multi-class classification involves predicting more than two categorical variables, right? So A plus, B, right? Whereas multi-label classification involves associating multiple labels or multiple outcomes, right? In the final result. So there are instances where the final outcome might be associated with multiple variables, right? These things that you're interested in predicting. And a very classic example that I normally give is if you're looking at text, right? On Stack Overflow, for instance. Stack Overflow is a classic example. If you go to Stack Overflow, what you will notice is that the questions, right, on Stack Overflow would typically be associated with tags, right? Those tags could be keywords that will help people that are looking for questions on Stack Overflow to, I'm just going to look at, let's say, machine learning or something. Let's see if we can find a question to do with machine learning. The tags would be, there we go. I'm going to go here. If you look at this question, right? This question is associated with multiple tags, right? So if you look at the question, what is the difference between supervised Oh, this is interesting. Supervised learning and unsupervised learning. So probably the person who asked this question tagged this question to be associated with machine learning, artificial intelligence, supervised learning, and unsupervised learning. So if we were interested in building a model that is able to automatically associate tags to questions on Stack Overflow, that would be a multi-label classification type problem, because the model would have to be implemented in such a way that you identify all possible tags that you'd associate to such questions, right? So the final output could be one or more labels, not just one unique label, which is the case for binary classification and multi-class classification, right? The final output can only hold one value, whereas for multi-label classification, the final output can hold multiple values, right? One or more values. But anyway, I thought this was really interesting. Yeah, this is really interesting. All right, and then in terms of unsupervised machine learning, we did mention that we'd focus on clustering. So clustering is a form of unsupervised machine learning which is really tied to pattern recognition. So the idea behind clustering is you group the observations. Remember, we are no longer working with a labeled data set in this case, right? As opposed to supervised machine learning techniques, right? The key thing with supervised machine learning, regression and classification, is that you should have a labeled data set, right? Labeled data set that you split into training and testing, and then the training data set will be used to implement the model, the testing data set will be used to evaluate the model. Whereas with clustering or unsupervised machine learning, you don't have a data set. The only thing you have are the observations themselves. And the idea is you want to identify patterns associated with the observations that form or comprise a wider universe of the data set you're working with. And all you do really is you group the observations. An example that comes to mind here is, I believe we have, I hope we do here, predicting, I think so. The student data set that we're working with, right, could be used as could be used to try and do some unsupervised machine learning. So a classic example of what we can do is we can look at the Moodle interaction logs, for instance, right? So this graph here is showcasing and I think this was this was done using clustering actually. So what we did was we got the observations for the Moodle interaction logs, and we created clusters. All right. So as part of K-means clustering, what you do is you, I think we showcased the so-called elbow technique in lecture series number 7, which allows you to determine the optimal number of clusters associated with your data set. Right. So in our case, for the data set associated with student learning outcomes in ICT 1110, what we realize is that there are 4 clusters. And if you really, plot, if you plot those clusters, you notice here they're color coded differently. You will notice that there are groups, right, that have manifested themselves, right? So we have a cluster of students falling in this group here, right? We have yet another cluster, right, of students falling in this group here. And this is an automated process, obviously, right? You don't manually do this. We have yet another cluster of students, right, falling here. This is, again, this is really all based on the attributes, right? The data attributes. This is not a labeled data set. all we are doing is we're trying to identify a relationship that exists between Moodle interaction logs and what do you call this? The final exam score. There's a cluster there, and then finally we have, excuse me, we have another cluster here, right? Yeah. And the idea behind this is, if you look at this pattern and you give this, if you look at these clusters and you give this to an expert, maybe the course instructor for ICT 1110, the course instructor will perhaps be able to explain the behavior here, right? We see some pretty interesting patterns, perhaps related to the frequency, right, of accessing Moodle, the engagement with the course. We see that there could be some sort of a correlation between those that engage more with the course versus those that don't, right? We can see here that the vast majority of people fading, those in red here, are those that will access Moodle less frequently, right? Anyway, the point is you're recognizing patterns, right? Or groups, and that's the insight that you're looking for. You notice here, if you look at this example, whilst we are interested in predicting whether a student is going to pass or fail, but as part of the EDA process, we are leveraging unsupervised machine learning, right? Identifying clusters associated with a specific data attribute, engagement. Again, so clustering is a classic example of unsupervised machine learning technique. So you organize the input variables into an efficient representation that will be able to best categorize them or characterize them. So you're forming groups. And unlike the supervised machine learning techniques that we discussed, so that's linear regression and classification, both binary, multi-class and multi-level classification, you don't really need labels, right? So you don't have predefined classes. You don't know what you're looking for. You're trying to find patterns, right? And the reason why you might be interested in finding patterns is different. Again, if to take you back to this particular graph, part of the reason why we were plotting this is we're trying to determine if there was some sort of correlation that exists between accessing Moodle, which is engagement, and the final score, which is the exam here. And by the way, the exam is a really horrible dependent variable to use in this case. I'm guessing the pattern would be different if we used specific test scores, for instance, maybe from test 1 or test 2 or something. But that's fine. Usually as a final outcome with clustering, you'd be able to uncover relationships that you wouldn't have known existed. So rather than you mindlessly developing this model that will assume that Moodle hits or interaction logs from Moodle best variable to use, what you can do is you do a bit of clustering to better understand, right, the sort of relationship that exists. So using this graph, some interesting insight that you can generate is perhaps to say maybe further drilling down to look at additional characteristics associated with these observations might help uncover other things, right? So it may not be enough for you to just look at a relationship that exists between access to Moodle or engagement with the final exam. Maybe you might want to combine engagement with a course minor, for instance, right? Or engagement with maybe sponsorship status, right? And perhaps the groups that you'd come up with would be more nuanced in that case. That's okay. This is two broad categories of clustering. So there's non-hierarchical and hierarchical clustering. So in non-hierarchical clustering, the relationship between the clusters would be undetermined, right? So you don't know them. Whilst in hierarchical clustering, you repeatedly link pairs of clusters until every data object is included in the hierarchy. So like I said, we are going to really, in the example, we are focusing on, we just want to get an appreciation of how clustering works. And so we focus on so-called k-means clustering. It's a classic example of a non-hierarchical clustering approach. So the way it works is quite simple, really. You start off by selecting the appropriate number of clusters, right? And you do this by, the way it works is you randomly, you set random centroids, right? So centroids would be the centers of the different clusters or groups, right? So the central point that is linked to all the observations that are associated with a particular group, ideally. So you randomly set these, and the way the model works is you continuously reassign these different observations to the closest cluster, right, by looking at the centroid. And you compute the new cluster centers as mean values. So ultimately, you get to a stage where you would have all observations linked to, so in this case, maybe the centroid could be somewhere here, right? So we're saying that the centroid would be the point where each of these different observations here are most closest to. So you continuously reassign centroids associated to these observations until you come up with an optimal configuration. The same applies to a centroid that would be associated to this group, for instance. So initially, when you set out, right, you just randomly assign centroids to these observations, right? Then you continuously tweak the model until you get to an optimal configuration, which is the case we have here, right? So again, these models would be associated, these observations would be associated to this centroid. We did highlight, I believe, in lecture series number 7, how you use the so-called elbow plot to determine the optimal, or to determine the appropriate number of clusters associated with your data set, right? So we'll see in the Jupyter Notebook that there's a way of plotting this elbow plot, right? So you generate this elbow plot, and then a human evaluator will be able to come through and check to say, well, this is where the elbow actually manifests itself. And so we see that we have 3 clusters for this particular data set. All right, so I'm going to share the notebook. Again, I want to insist that we find time to look at the Jupyter Notebook, and then we can have a discussion centered around the notebook when we meet. Is it next week? Thank you very much. What you'll notice, by the way, in the notebook is that the notebook is split up into distinct parts, right? So there's a section. There's a section which is going to look at regression that involves the use of a single variable. Another example that uses regression that uses multiple variables. So we'll look at an example of univariate linear regression. And then we'll look at multivariate linear regression. And then there are examples associated with binary classification, multi-class classification and multi-label classification. And then finally, we have a section that will look at k-means clustering. All right, thank you very much.